Okay, I believe we are live. I failed to prepare properly, so I'm not 100% sure of that. Let's see if my smiling face is on the screen. It is. Okay, so this is the first office hours for CSE598. For those that are catching this video as a recording and not as a stream, this stream is in support of pwn.college, which is a free and open website. You can go to it right here at pwn.college. And as it says on the page here, this is a website where you can learn how to hack. It is a site that puts out a bunch of educational material. A lot of it comes out of Arizona State University in support of a number of university courses. If you want to follow along or engage with the material, you certainly can. You can create an account. It is free. We just ask for an email and a password. We only use the email so that we can send you your password if you forget it. As far as how does the site work, if you read on the homepage and follow along this video, it'll tell you how to get started. In short, you can go up here to dojos, which will list a series of topics in increasing complexity and difficulty, as well as ASU courses that select challenges from these topics. I do see you guys there in Twitch. It is good to see at least one familiar name. I don't know if I recognize the other one. And as I mentioned at the beginning here, this stream is focused on CSE598 for the spring 2024 semester. Now, this is the first week of the course, and we are doing system security, doing like a review of kind of prereq material. And there are challenges listed here on the website, as well as lectures, although this particular module doesn't have pre-recorded lectures. So we have the first stream, as well as the slides that are there, and then this is the first challenge that was assigned. If we click on practice or start here, it should pop up and say that a challenge is started. From there, we can interact with these challenges in a couple of ways. Up here at the top, we have workspace and desktop. Workspace gives us a VS Code-like interface right here in our browser where we can work. If a desktop is more your speed, we do have kind of a VNC interface here where we can interface with the challenges as well, right in the web browser. Me personally, I prefer working in a terminal. So you can also connect to the dojo over SSH once it's set up correctly, which is described in the video here. It's sshhacker@dojo.pwn.college, and this will give me a shell in this challenge environment. Every challenge environment places some type of binary or challenge, and it will be located in the challenge folder. In this case, there are two binaries, a userland binary and a kernel module. In the end, the objective is to cat the flag, but you can only do that if you have root permissions. So there is some way to leverage whatever is in the challenge folder to get elevated permissions and then cat the flag. With that, I'll turn over here to Twitch. I see a couple hi hellos. So office hours in general are open-ended, right? I mentioned on the first day of class that the style of education here is kind of a flipped classroom, which means you ask questions, I then answer. So if you are on challenge 2, challenge 3, and you're like, hey, I'm stuck, I don't get this, I don't know how to think about this. This is the time to ask, and I can pull up the challenge, take a look, and discuss the concepts that are at play. That's kind of the design of office hours. Now, this module is a little bit different because it is a review. There's not pre-recorded lecture content already included in there. So hopefully people are somewhat aware of what's going on. The question is: the global buffer overflow on Toddler System 3 intentional? Well, let's take a look at Toddler System 3. Let's talk about it. In general, I would say we're probably aware of what we did. So the answer is probably yes to any question like that. Although historically, we have seen challenges where there are unintended solutions. Most of the time, we don't patch them as long as they are technically interesting. Right now, if it was something silly like, oh, you can just cat the flag, right, on a level that's supposed to involve user land and kernel and memory corruption and race conditions and these type of things, well, then we'd probably fix it, right? If we just accidentally made cat set UID. But for things within the challenge, as long as it doesn't completely negate the challenge, we either intended it to be the case or are aware of it and have chosen not to patch it because we think it's a valid solve, right? One of the things that I know is mentioned on the meme channel is flag is flag. And what that means is just because I solve a challenge a certain way doesn't mean that's the way you need to solve the challenge. For a lot of these, particularly in this course, less so in some of the earlier classes in kind of this progression here on the website, where there are simpler concepts, right, or foundational topics that you're learning about, it becomes a lot more difficult to apply creativity or like apply your technical knowledge in a unique way. But as we get to these later challenges, it absolutely becomes something where you start obtaining the ability to arbitrarily write or arbitrarily read. And how you apply those primitives is going to be very different between everyone, right? Now, there's definitely some common things, but the number of ways to gain elevated privileges expands, right? Because you're working with more complicated, more powerful things. So I see a second question here. Can I help with 2? Do I go ahead and create multiple children? So that will be exploiting time of check, time of use on state signal inside Yon85 set count, validate func in kernel module. Okay. So I tend to take questions in order. The first question is the global buffer overflow on Toddler Sys 3 intentional? So here is Toddler 3. I believe I'm on 3.0. In general, I'm going to work on the 0.0 challenges just because it makes it easier to discuss and demonstrate topics unless you specifically call me out and say, hey, let's do this on a 0.1 because there's a big reason to. And so if we look at the user land binary here, what we see is it accepts a network connection. It looks like we have a bind. It's going to open up 15 YPUs. Right here, we're going to set comp. And we do have a fork server. So this right here, if you're not familiar, is that's not a fork server, it's a thread server. But it's a fairly common pattern in network applications where you have essentially an infinite loop here that's going to call accept. It's then going to spin off a thread or a fork. And so this is a common pattern that you see in multiprocessor, multi-threaded applications. So the parent thread in this case, or the main thread, will loop back around to while and block on accept, while this P thread that gets created will spin off and call this run thread here. Run thread, it looks like it is doing Looks like a little bit of I/O rerouting, probably changing standard in, standard out to be the network connection. So the set vbuff is going to deal with buffering. And so like if we don't know what set vbuff is, we can man set vbuff. It's not a Robert stream if I don't show you a man page. And this is making it so that this network connection will not be buffered, because buffering is pain. As we go here into the challenge, we can take a look about what's going on. We have a few different things we can do. We can load a program. We can init a YPU, run a YPU, or quit. If we go down a little bit here, I do see, Twitch chat just wants to get right to it. The buffer overflows when it reads hex 1000 bytes in the challenge function. You know, we're almost there. We're almost there. And right here, we do see a read of V1 into this memory location of hex 1000. And so then the question is, well, how big is this buffer? Right? Here it is data plus 768 times V3. Now, one of the things about decomp is it's ugly, right? And so you have to kind of apply you have to do one of two things. You either have to go through and fix up types and like define regions of memory as an array or as a struct, and you can start to make this pseudocode clean up and look a lot more like C, or you can learn to read ugly pseudocode. And if we look at this, this is a pointer, and then there is some offset of 768 into it, times an index. So we can think of this like an array, where this V3 is the index into the array. Now the size of each member here is 768. So this immediately should make you think, hey, there's a buffer overflow here. Now, upon first glance, there's a buffer overflow from, for instance, and we see here this V3. If I click on this and it's highlighted, this V3 is something that we control. So when we run load program, it's going to call scanf and be looking for a number. That number will be stored in V3. As long as V3 is less than 15, because hex F is 15, if it's greater than 15, I guess it could equal 15. But if it's greater than 15, then it's going to throw this assertion and bail, right? But if it's 15 or less, then we do execute this line right here, where V3 is the index that is being multiplied by this set 768 from this data base pointer. And so that's somewhat interesting, right? We could overflow from index 0 to index 1 or index 1 to index 2. But when we start thinking about like, well, is that interesting? Well, as a user, right, as a normal user of this, where is data expected to be written? Well, it's supposed to be written clearly in the first 768, right? And it's supposed to be written in the second 768, and so on and so on and so on. Until we get to the 15th argument, the very last argument, or last item, right, in this array. The 15th item in this array is 768 in length, but we can read in hex 1000. So we can read in a page of memory. And hex 1000 is a heck of a lot bigger than 768. And so if we look at this 15th index, how far does that allow us to write? And what values are located at those locations? The question is this intended? This is an absolutely critical component to exploiting this challenge, at least via the intended path. Because writing far beyond this base address of data will allow you to perform a buffer overflow and influence some other values that exist in memory. All right. So I believe the person that asked 3 is satisfied. So now we'll take a quick look here at 2. Let me read the question again here. It says, can you help with 2? Do I go ahead and create multiple children to be exploiting the time of check, time of use? And it says on state.signal. I was following where we were going until state.signal, but I don't have every challenge memorized, so let's see what we got. Okay, so we open her up, we mash tab, because that is the single most important key in IDA. And we see the same pattern that we saw in 3, so it's not worth going into... No, it's not. It's not the same pattern. It's similar, but it is not the exact same thing. So in this case, it opens up a single YPU. It tells us what file descriptor it's on. It is going to mmap some region of memory. Hopefully it's not mission critical. Well, from this assert message, we can see that its use is to be the location where shellcode is located. So that helps. Helps us just have a mental model of what's going on. Just going to pause for a moment. I got another question here. We'll read it and address it after this one. It says, if we have time, I'm curious about 6. You're trying to do a buffer overflow, but it's getting set comped with syscall 20, which is confusing because they're not sure why write v is being called. Okay. That one will be interesting. I don't think anyone's asked about 6, so I haven't looked at it in the past week. So let's see what happens there. But returning to challenge 2 here. We know that there is some region of memory that's getting mmapped. Semantically, it's going to be used for shellcode. The challenge says it's done that, so I should have read ahead. Mapped hex 1000 bytes for shellcode, and then it's going to call read on that address to give us hex 1000 bytes. It then tells us that it's going to execute our shellcode. However, prior to doing so here, we have setcomp. This is real setcomp. There's yon85 setcomp and then real setcomp. They work and function a tad bit differently, as you'll find in level 3. So this is real setcomp, and it looks like we are allowed to use fork, we're allowed to use mmap, we're allowed to use ioctl. So one of the things that is a good way of kind of marching forward in these challenges is to look at what's different compared to the previous one, right? And I believe that's kind of where the intuition came from here is in the first one, I believe we were in level 1, we were restricted to ioctl and mmap, right? And we are able to use multiple... Was it multiple connections? I don't remember if it was network. No, I think level 1 we just wrote the shellcode and it was single threaded. Now that I think about it, but in any case, here we are allowed fork, mmap, and ioctl, and this right here is not multi-process, and it is not multi-threaded. So that means we can only have, at least when we start, one thread or one process executing. But as you point out there, Twitch chat, since we can call fork, we can call fork and create child processes. But since we are limited in our how we can influence execution to our shellcode, we're going to have to write shellcode that calls fork. And the question is, why would I want to do that? Because that is the end of the userland binary. And you're saying there's a time of check, time of use trace on state signal. So I'm going to assume that that is over here in the kernel module. And we'll click all the buttons. We hit the all-powerful tab. Well, I see state signal here, but I don't know anything about that yet. We just had, this is just wherever IDA dropped me. When we're looking at kernel modules, is everyone familiar with how to kind of reason about kernel modules? As far as like where are entry points or how to think about execution flow if we're looking at a kernel module? I'll give a moment here for Twitch chat to catch up in case anyone says, hey, no, Robert, give a small rant. If not, I'll just carry on. One person in Twitch here says device ioctl is basically your main when you're interacting with kernel modules. And that is not what I would say at all. The thing to kind of think about here, like for these challenges, device ioctl certainly plays a key role, right? I get why you would say that or why you would think in that manner. But kernel modules really have many ways of kind of interacting with them, right? And so if I were to call ioctl on the file that this kernel module exposes, then this is what gets executed. But if instead I called, for instance, mmap, which I believe is on here somewhere. Let's see if I can read today. Is it? It is. Device mmap, then this is what gets executed. Now, the fact that this kernel module's device mmap does this and this is a specific implementation detail of this kernel module. There's nothing stopping this kernel module from having you call mmap on the file and it suddenly starts doing a whole bunch of crazy stuff inside the kernel module, right? It's probably not convention, but it absolutely could be the case, right? So like this device mmap, what's going on here? Well, if you've solved level 1, you've figured out that when you call mmap on these kernel modules here, in this particular case, it's going to print out something, and then it's going to return a pointer to this private data, right? And this file object here represents the file of the kernel module. So this private data is like a shared region of memory that is actually accessible within the entire kernel module. We see it again here on device ioctl, right? Where this private data is being used. Well, what happens when you start up a kernel module? Well, it's going to be a init module. And if you were to, we're in this right now, VM connect, and then just run dmessage, we see this welcome. That's unfortunate. We see this welcome output, right? Where does this come from? This comes from a init module. When the kernel first starts up, it initializes the module, and this is executed. So there isn't a single point of where execution starts, right? The kernel, aside from a init, right? Where the module is first like started up. But depending upon what interface the kernel module exposes, there could be many ways to trigger behavior within the module. And so there's many places where execution can begin depending upon what's happening. Right? Like there should be, I imagine, device open. Yes. And here we see when open is called on this device is when that private data is initialized, right? That's when it's mallocked inside of the kernel. So if we jump back to the userland guy, does it, when it opens proc YPU, before you even send your shellcode, this open call on the kernel module here on the file that's being exposed, when that open is called, the kernel module is going to call vmalloc, and that's going to allocate the memory that is the private data. That's what ensures that there is a region of memory to remap when the mmap occurs. Now, circling back, because I had a little bit of a ramble there, the question that we had was that there's a time of check, time of use on state.signal. So we took a look at device open, we took a look at device init, we have some understanding of what's going on with device mmap. So that brings us back to device ioctl. And it is fair to say that this is where a lot of the action is, right? We have device ioctl. Looks like we have a bunch of local variables here. This state looks pretty interesting. And we see that there's a check. There's an if, and if we don't hit this, where do we go? We just return. So the first thing we have to recognize is that there is a check to really trigger any meaningful behavior here, that this command value must be 1337. And if we click on command here, we see it's highlighted here, it's printed here, but this isn't particularly useful because this is a print statement. And so we can look further up and we see device ioctl. It is the second argument of device ioctl that needs to have this command value. And so if we set that to 1337, which we absolutely can, we can trigger this behavior. Looking a little bit further here, assuming that we've done that, this private data comes back into play. And remember, we do have access to that private data. And so we can write whatever we want here for the private data that then gets stored in state.code. So far, so good. This is very similar to what we saw in level 1. Now, this is where things get weird. Right here is our while loop. This is our kind of interpreter loop for these Yan code bytes that are in state.code, assuming that we put them there. This check is if the instruction pointer is 255. If it is 255, we've kind of reached the end of instructions because there's only 255 bytes that are going to be interpreted. And so this is kind of we've reached the end of the instructions. We're going to just return 0. Assuming that we are not on the last instruction, there is a Yan85 seccomp validate, and it's going to validate this state. This is if state.signal, then we break. Otherwise, we're going to grab, this is going to be the byte at the instruction pointer, the Yan85 or YPU's instruction pointer, because this is a post increment. So we'll grab the value and increment the instruction pointer. That value then, what do we got here? Okay, we're shifting it. So what is this? What's the type of this according to IDA? We go back up. It's an instruction T. That's convenient. Can I see what an instruction T is? Okay, so it is 3 ops. Okay, so that consists of the 3 yarn code instructions. Okay. So then we'll interpret that instruction given this state object. And we've seen how interpret instruction works. I don't think I need to go down that rabbit hole. Twitch says, sometimes IDA gives us nice things, although sometimes I found instruction T to be misleading in terms of the argument order. I would believe that. Like most tools that stray too far from the purity of assembly, I have a hard time trusting. They can be great when they work, but when you trust something and don't validate it, you can spend a long time believing something that's false. So that's a good tip there. So we already know how interpret instruction works. We have some idea, right? This is the VM interpreting the instruction, updating the state, and would loop around. So then the only thing we haven't looked at is this setcomp validate. Setcomp validate. It is going to grab the instruction T at the instruction pointer. It's going to take a look at the argument, and we are checking if this argument is hex 20. And then we are also looking for this argument to be hex 18. So let's see if we can make sense as far as what is this setcomp validate checking. Yeah, Twitch says, do not blindly trust the dark magic. So, like, it's great, and these tools have come a long way. And so it's like it's a trust but verify, right? And so we see here, just at the beginning of interpret instruction, what are we doing? We are checking this instruction value, and if the instruction value happens to be 20, then we're going to call interpret sys. And then within interpret sys, we need to look. What was the other value? 18? Well, we don't see hex 18 here, right? And so that may immediately make us think, hey, what's going on? Okay, I got something from Twitch here. What do we got? Read syscall is what setcomp is filtering out for level 2. Open is working, though. They're not sure about write. So I'm going to guess, and I could be wrong here, that you know this because you tried it, right? I want to think about it in terms of the bytes. And we saw hex 18, right? And these comparisons, including the comparison for hex 18, was done in a specific manner. If we go back up to setcomp validate, it is performing an AND. And it's checking if that value is non-zero. So what we should see is that read doesn't work, which is what you say, because hex 10 ANDed with hex 18 will yield you hex 10. The other value, so that prevents us from calling read code, which is what we see right here. The other value that's being filtered out would be whatever is right here, read memory. Why is that? Because hex 8, or 8, because hex 8 and 8 are the same number, 8 ANDed with hex 18 is going to yield you 8. And so that's going to be a positive value. And so we are not allowed to call read memory or read code. And that's what setcomp is filtering out. And that's how it's filtering out. right, is by checking the result of this argument ANDed with hex 18. And then checking if this argument is ANDed with hex 20. So to go back to where we started, there is a time of check, time of use race. Now, where I think the original question went a little astray is they said the time of check, time of use is on state signal. And it isn't on state signal, right? When we say that a time of check, time of use is on like a particular resource or a particular memory address or a particular location or value, right, or a variable, what that means is that is the critical resource that is expected to not change by the code. If state signal is set, it's set. We can't change that or influence it. And if state signal is not set, then it's not set, right? I mean, we could trigger it, but we can't untrigger it from here. So the race really isn't on this state.signal value. The race is a time of check, time of use. The time of check is right here on yon85 setcomp validate, right? If when yon85 setcomp validate looks at the code, looks at this particular yon85 instruction, and it passes this check, then we're good. And the assumption that the code makes is that the yon85 bytes will not change between this check and this use. And so the race is really on state, where is it? State code? Yes. On state.code. And so what we'd need to do is we would need to have, I would go with two processes in total. I think you can pull this off with a parent thread and a child thread. We do not need multiple children. We just need both processes to be efficient in what they're doing. Now, the first thing that we know we want to do is we want to trigger this ioctl. We want to cause execution to occur repeatedly and often. Comment from Twist Chat says, I thought that it's a very small window and it's probably not the correct solution. So my opinion in general is to try and keep things as simple and straightforward as they can be, and then only make things more complicated, right? Only involve more processes or more threads or more complexity in your exploit code once you've ruled out kind of the simple approach. And I know you can solve this with a parent process and a child thread. And I only know that because I did it for like a 466 office hours a couple months ago. Let's see. I'm sorry, I got lost a little bit here. Oh yeah, I was responding to the question about it being a small window. So keep in mind that when we're talking about like time windows and things like that, you're looking at this in C code. But we really need to think about things in terms of like what's going on at the assembly level, because these time measurements that we're racing are extremely, extremely small. 3 lines of C could be forever in assembly code. So if I go back here to the device ioctl, hopefully I hit the right thing there. If you saw, I right-clicked and then said synchronize with the IDA view. I want my pseudocode here to be synchronized with the assembly so we can take a look at it here. And if we look at, I'm going to click on the yon85 set count validate function. We go over here. Right here is the yon85 validate function where that gets called, right? And so we can pass the check. How many instructions get executed before interpret instruction? Right? We'll assume that we pass the check. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I don't know, roughly 20, 25, right? And these 25 instructions, I'm not going to say any of them are exceptionally slow, but a number of them involve dereferencing memory, right? Like this right here is a fast instruction. This right here, this move 0 extend edx sil. And the reason I know it's a fast instruction is because this instruction only needs 2 registers that are on the CPU. It doesn't have to grab a value from memory. It doesn't have to go out and reach anywhere else. But when we see these LEAs and we have these open brackets where we're dereferencing something from some pointer, in the context of the CPU, right, these are extremely slow instructions, which we'll explore in a lot better detail in the next module. But it's worth mentioning right now. Right? So there's about 25 instructions there. And for argument's sake, I'm going to say some of them aren't the quickest. And so if I have one process that is triggering execute, 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 then we can think of that as running through from set count validate to interpret instruction back to back to back to back, right? Well, what is the other process going to do? The other process is going to strategically target one of these 2 values, right? We'll initially, because it checks that both of these conditions are met. So we could write it with, for instance, 20, and then what would be a valid argument? Yeah, right works. I don't know that I'd want to call open repeatedly, but we could. So right or open. So we could give it 2 or what is this? 1, right? And so we'll initially have good code in there that has the values 20 and then 1. And that will pass this check. And our second process is just going to take that one byte, and it's just going to switch it between 1 and then 8, or 1 and then hex 10, right? Whichever value it is that we want for our exploit. And it's going to do that just back and forth, back and forth, back and forth. What does that look like in our assembly? No, I can't do it there. So we'll just have a random Vim buffer for this. So what instructions would I want in my second process? My second process is going to be assembly. So I'm going to have some type of label, right? We are going to assume this is not how you make comments in assembly. This is just me kind of scribbling stuff out to hopefully kind of finish conveying the approach or the tactic here. We're going to assume we have a pointer to the hot byte in, I don't care, RDI. RDI is good. So we're going to say move RDI. We said hex 1. We probably have to make that a byte pointer. That makes it past the check. Move byte pointer RDI. We'll say 8. Then we jump to the loop. Right. How many assembly instructions? And this may not be valid assembly. That's fine. How many assembly instructions are we executing to perform this swap? 3. And it's 3 in a loop. How many does it take to change from a good value to a bad value? 1. And so in the time span, right, we can be insanely fast. In the time span from, did I lose it? I did lose it. Here to here, where there's 25 instructions with a large number of memory accesses, our process is going to be executing maybe 3 instructions. And so that means that, assume that they all execute at equal speed, we're able to run our 3 instructions, 8 times before this even makes it there. We are so fast that we can change it, and it's fine to do this. Sometimes it'll be a 1, sometimes it'll be an 8, right? I don't care if I miss it sometimes, if I lose the race, and I got caught by setcom. Oh well, I only have to be right once. And by taking this type of an approach and just being so fast that it's essentially a 50-50 shot by the time we get down here to interpret instruction, if it'll have the illegal byte, we're going to hit it almost instantaneously from our viewpoint, right? In human time. And so that's how I would approach it. I've talked to some students and they've said, hey, I need to spawn, one process to write it as 1 and another process to write it as 8. And you can do that, right? And it will work. The reason that I would suggest to not do that is because now you have created more complexity in your exploit, because now you're calling fork more than once. You're managing more than one process, right? And so you've added more points of potential error or potential failure, right, in your exploit. You'll find, as I write exploits throughout the span of this course, almost everything I write is quick, dirty, simple, and I throw it away. And I do that because it forces me to repeat and practice these patterns, right? So then when I look at something, I kind of know this is the approach that I want to take. Why? Because I've written it so many times before, and I've used this type of reasoning. Does that help the person that was asking level 2? If not, or if so, I guess, I will move on. We can take a look here at level 6. Okay, so that was good. Awesome. Like I said, guys, this is what office hours is about. This is what future class time is going to be about. I want you guys to have questions. The best thing you can do is, if you have like a real doozy, is hit me with it on the Discord. And if it's something that's particularly interesting, we'll in class like run through some type of code example or demo to kind of discuss whatever it is that came up. But this is why it's important that you guys have the requisite knowledge, right? So when I say you need to understand shellcode, it's because we're going to be writing shellcode, right? Or where you need to be able to talk about x86 assembly in order to just have discussions in this class. Okay, so if I remember right, let me scroll back up here. If we have time, I'm curious about level 6. I'm trying to do a buffer overflow, and it's getting set comped with syscall 20, which is confusing because I'm not sure why write v is being called. All right. Yeah, we're getting there. One of the things that I know this person is aware of, but as I get to later and later challenges, I become less and less helpful. And that's because the later challenges are meant to be challenging. There's usually some type of trick or some type of, nugget of wisdom or intuition that you're supposed to kind of stare at it and struggle and then think and then realize. And it spoils the later challenges if I just kind of give it away. Now, if with the earlier ones, like the discussions we've had on 1, 2, and 3, otherwise, as Twitch chat says here, otherwise it'd be called trivia, right? But these earlier ones where we're refiring the synapses here and remembering how race conditions work and how kernel modules work and chaining stuff together and thinking about things like this, like let's talk about it, right? These are good things to make sure you understand the concept. And these later ones here, and I don't have the last two, there's not a hard rule, right? But the later ones here are meant to be challenging. And so just know that I will be less helpful as you move later in the material. All right, so let's see if I can make sense of what we got here. I'll hit tab, the almighty button for IDA. Okay, what do we got? Says this challenge is listening for connections on 1337, so it's network. We see bind listen. Are we a fork server? I don't know yet. We're going to open 15 YPUs right here. Restricting syscalls. What do we get? We get set robust list. I've never needed to call set robust list. If you're curious, I think this is here to prevent a bug, like a potential error state that you can run into. Set robust list happens when you spawn a new process. It's part of the initialization step there. We have, if I remember right, could be wrong. We have exit group, so that's, I don't think, particularly useful. Is that really all we get? Set robust list and exit group? Brutal. Oh, wait, what is this? If 22... Okay, I'm told we get a lot more later. All right. Well, 273, we go back here, and that's where it gets added to be excluded. So that's a bummer. Okay. Oh, there we go. I just have to keep scrolling. We get read write, we get close, we get dupe 2, we get accept, we get clone. We get wait for. Okay, we're all over the place here. All right, set comp fires up here. Okay, this one is a fork server. You can ask anything you want, right? You just have no guarantees about what I'm going to do, because I don't know what I'm going to do even. So this one is a fork server. When I said that's a kind of a common pattern, where the prior one was a threaded server. So we see that infinite loop, we see accept, and then we see fork. And if fork is 0, which 0 means the child, then we will break out of this while loop. And so the child is going to continue down here into do2, close, challenge. The parent, on the other hand, will not break. It will close this socket, and it will call wait. And it is going to call wait on 0. It is important, if you don't know what wait is, or you don't know what anything is, the first place you should look is the good old man pages. Well, you can try Sense AI. People asked, but Sense AI hallucinates and lies. Man pages, that's right. Every time. And so one thing that we may want to know is, what is the significance of 0 on wait? And I don't know if it's significant to this particular challenge or not. But we have wait. We can hit the / character that you see here in the bottom left. That allows me to search. I'm looking specifically for wait. I hit enter. I mash N a couple times. This is going to allow me to go to the next instance of what I'm searching for. Wait. Okay, this is probably what I want. The wait and wait PID. The wait system call suspends execution of the calling thread until one of its children terminates. The call wait status is equivalent to wait PID, W status 0. And if we look at wait PID, what is that? 0. That is the options, so we can search for options. And the value of options can be any of these things, not particularly interesting. So then the other question is, what is wait 0? Okay, what is the significance of the -1 here, which is the equivalent here? So it's going to be the first argument, which is the PID. So we can search PID. We get down here, it says the value of PID can be, if it's -1, it means it will wait for any child process. Right? It does not need to be a specific child process. And these are the type of details that you'll only find by reading man pages, right? So what goes on with the child process here? Well, it's going to call challenge. Is challenge doing anything interesting? The server will allow you to schedule computing tasks on YPU. Okay, so this is a very similar interface to what we've seen before. I haven't gotten to what was the question headed there? It was like something about write V, right? Yeah. I haven't made sense of write V yet. Okay. This guy has load program. This read looks interesting. This could just be IDA being confused, right? But here again, we see some type of an array. And IDA could just be confused on the types. But we have some type of array here. With a large read. And so this is, again, something that I'd want to look at. My personal preference is to use GDB. I like looking at memory that's actually running and kind of verifying what I have going on. But there's potentially a buffer overflow there. Doesn't mean that there is, and it doesn't mean that if there is, it is useful, right? It's a suspect large read. You were wondering how long till I mentioned GDB. I don't plan on using GDB today. Unless there's like a good reason. So that is something worth looking at. What else do we got? Now, I remember we only have one line of execution here, or one thread of execution at this point. So I can't really race anything yet. So we'd have to, I'd be really curious what I can get from that overwrite, or that potential buffer overflow here. Like, what could I influence? And while GDB is great, I did just have a... Yeah, exactly. Twitch chat said you should try exploiting that read and see what happens. I did just have a little rant here a little bit ago about using the simplest method possible, right? And there is nothing simpler than simply throwing stuff into a program and seeing what happens. So let's give that a try. So if you're unaware, I'm using IPython. You should write a script. Just working in IPython is pain a lot of the time. So I would encourage you to write a script and run it rather than use a interpreter, because it's easy to blow your leg off and you shoot yourself in the foot. There's a lot of foot guns. We'll see if I do it. And I hit Control O to get these additional lines, if you're not sure, weren't aware. So we'll say from pwn import star. We'll do some boilerplate here. Context arch equals AMD 64. In this case, I want to have a remote. I know I want to go to localhost, which is going to be 127.0.0.1. And the challenge says it's TCP port 1337. Cool. We have that. Now, what can we send to it? Well, where was our overflow here? It is on load program. So, how is it taking this value? It's calling scanf. It's always important to pay attention to what syscall or function, I guess, is being used to take in input. If this were a read, I would need to behave differently than if it's a scanf. Scanf is going to take this format string right here, and it's going to search for a value that meets this requirement, and it will end that search upon encountering white space. For that reason, I'm going to use sendLine to pass this value of load program, because sendLine will send the value followed by a new line character. The new line character qualifies as white space, which should cause scanf to return, storing the string load program in S1. Let's see, Twitch chat. All right, we got some more chatter here. IPython's fun for testing out ideas, but not for writing solves. They themselves have personally lost many hours of work trying to use IPython. And I 100% agree with you there. Like, if I were trying to write an exploit, you would see me have a side-by-side Vim and then kind of an execution terminal. But in this case, we're just going to try and throw some bytes into this and see what happens. So we are going to pass load program to it here. That should satisfy this comparison. At which point it's going to scan again. It's going to call scanf a second time. This time we're looking for D, which is going to represent a decimal or integer value. Actually, how does D stand for integer? Whatever. That's the convention. So I need to pass it some number. This number looks like the maximum value is 15. And now, very similar to how I was describing my thoughts on the overflow that existed in the earlier challenge. In this challenge, the thing that I'm interested in is how far can I overflow? Is it D for decimal? No. I don't think you can do a decimal with that, can you? Let's What is D shorthand for? No. Man 2 print F. Man 3 print F. Yeah, D4 decimal conversion. IDU. It's not. You can do decimal with D. No, it says right here, conversion special D. The int argument is converted into signed decimal notation. But if it's an int, then why is it becoming a decimal? Like, okay, so it takes integers, but it will represent it, allow us to format it as if it were a decimal. And then the default precision is 0, which is why it looks like an int. That is silly. Good call. Robert gets baffled by math words? Absolutely. I get baffled all the time, guys. Oh, okay. Oh, I missed some stuff here. I used to throw input at problems when they started off. Later on, I actually learned to reverse engineer and be precise. Not sure what's smarter. The smartest solution is the one that gets the flag, right? They're two very different skills. The first is technical knowledge and technical ability to perform the reverse engineering, which is definitely an important skill. But I would argue that a meta skill is knowing what not to reverse. That's particularly true, and oftentimes the pain point in this website's reverse engineering module, where people will spend a lot of time looking at assembly instructions that have zero relation to what you need. Right? The most important skill, in my opinion, when it comes to reverse engineering is knowing what to ignore. Because then you are only looking at stuff that matters. You can spend a lot of time being technically correct, like perfectly correct, understanding the functionality of something that is completely irrelevant to your objective. As far as, exploiting a binary or understanding it for the purposes of like a specific goal. That's definitely different than trying to reverse engineer and reconstruct source from a binary. Very, very different goal there. But anyways here, so we're going to send line. We said we're going to send a large value because I want to get to the end of this array. So 15 is the largest thing I can send. Let's send line 15. All right, it's beautiful. Next thing it wants is it's going to call a read, and it's going to call a read for hex 1000. So let's send, and we're going to use send, not send line here, BA times hex 1000. The best thing to end programs with, or your kind of I/O, is interactive, in my opinion. So we're going to go with an R interactive. Let's see what happens. Nothing. Nothing happened. Well, let's see. Did I done goof here somewhere? Or do we need to bust out the GDB to explore? Minor warning. Not important. Did I connect to the VM? No, I did not. Good call. I expected something to happen. The hex 1000 is a lot of bytes to write, right? And that is a good tip. That is something that should be on the Discord. Make sure you're on a VM practice here, because otherwise you're not inside the VM. Now, will this remember what I did? IPython, for whatever reason, is like insanely slow in the VM. sweet. So we will cheat a little bit here and say P is not cheating, but we'll launch the process inside of IPython instead of in a separate, what is this, 6.0? So instead of in a separate terminal. See what we get. Still looking pretty good here. Okay, so nothing crazy there. Question: does IPython need a bunch of RAM to do its magic? I don't believe so. So now the question is, well, what is going on here? Well, we can always trust GDB, right? And then one of the kind of debugging tricks. Yeah, so one of the comments was, did I remember to quit? So we can see, I don't want a GDB debug on that now. For this, we go right here. Okay, that's good. And the comment was, did I forget to quit? Sometimes the error is triggered when you quit, and that's absolutely true. And so if I type quit right here, we get EOF, right? So we don't necessarily know what happened here. Now, I don't see anything interesting there. So my next thing, the audit log is what popped up as well. Yeah, but like this audit log is there, but this doesn't like explicitly say, hey, you seg faulted, or it's just okay. There's this audit message, and I'm looking at it, and it doesn't immediately mean anything to me, right? Like this is an instruction pointer, and so maybe this is a leak that I could use for something if I knew what this was leaking. Somebody says, bro, Rob's reading messages before I even see them pop up in chat. Time to streamer is fast. Yeah, time to me is fast, but time to you is slow, right? So anytime I say something, there's quite a long wait. SIG31, you say, is you're not going to tell me, are you? Yes. SIG on x86 ARM 31 is SIG-sys. So you are correct there. SIG-sys, I don't know if there's other uses of SIG-sys, but SIG-sys definitely is used for SecCom. Now, is that related to anything that I did right here? Maybe. So what changed? Okay, so there is a change in the behavior there, but we have to reason about, well, what the heck is causing this, right? Oh, we could be on a wild goose chase, but we said we're going to take a simple approach, and what we've determined here, right? We have one audit at the end. If I do this, and I do not send my garbage, right? I just go interactive, and then we quit. We still get the EOF. We look at our D message. We don't get this audit, right? So we are influencing something here. And so the question becomes, well, what the heck are we influencing? Like what is happening there? Now, it could be a bunch of different things, right? The Twitch says, hey, there's definitely a correlation between these. And so we need to make sense of it. At this point, I would really reach for GDB, right? I'm probably not going to be able to reason about this statically, because what I care about is what is going on in memory. And I'm going to have a problem there. My tmux is outside of the VM, but I want to debug within the VM. So we'll get out of tmux here. We'll VM connect. We'll tmux. Now this tmux session is running inside the VM. Maybe. Okay, we have this. I'm going to do GDB debug. I guess I don't need the block right there because the child process is going to be hanging on interactive. Oh, but I need... Okay, now I'm a liar. I need... Before I connect... Okay. So I have GDB... Right now, it's attached to the parent process. My Python script here says waiting for GDB. It's blocked on this input line up here. So that means that my Python script hasn't yet connected to the parent process. And the reason for that is I want to observe the behavior inside the child process. So I'm going to, inside GDB, set follow fork mode child. And what that'll do is make sure that when fork is called, GDB is going to follow the child process. So now, once I mash enter here, that'll cause execution of the Python script to continue past input. So the script will now connect, trigger that behavior, and hopefully GDB catches something worthwhile for us. Did we get anything? Okay. So we got nothing so far, right? And where are we in this program? Well, we know where we are because we can look at this backtrace. The backtrace is like the call stack. So challenge called scanf. Scanf is calling a bunch of its internal stuff, which is calling read. Now, we know, because we know what our script did, that we are currently back up here reading for a command. And we saw that we triggered this behavior when we gave it the command quit. Right? But I want to set a breakpoint first, because I'm curious what happens when we call quit. Why does this behavior happen? Well, it says if it is quit, then we break and return. So ultimately what happens here is we return from whatever this function is. Is it challenge? It is challenge. So let's disassemble challenge. This is the ret that's going to happen after somewhere up here. Quit is compared against, and then we break out of that loop. I don't necessarily care where that compare happens because I understand the logic from looking at it in IDA. So I just want to set a breakpoint. So we're going to break at challenge plus 756. That's great. Now when we continue, our standard, what we type is getting passed into IPython, since we are interactive, which in turn is going to get passed and sent over the network. And what I want to send is quit. Okay, I'm in GDB. We continue. We quit. We quit. No good. We quit. Quit. So what's the problem here? Well, I can't get this sent. Right? If we fini quit, that input isn't making it there. So what we'll have to do is send the quit over here, which will still be fine because we can block with this input and set the breakpoint at the time that we're blocking. We're blocking the script. So set follow fork mode child. We'll disassemble challenge because I can't remember a number. We'll break at challenge plus 756. We continue. If all goes well, I go up to my Python script here. We hit enter. Oh, we didn't make it there. So we're still terminated by success. And we had that breakpoint at challenge plus 756. Well, maybe we need to set a breakpoint a little bit earlier. We said if quit, break. Let's see if we can find that string compare quit. What do we got there? We got a thumbs up. Seems good. You're seeing good things over here? Scroll back up. Did I miss something? Yeah, we still got this success. So that's an interesting observation. Twitch chat says, well, maybe there's a canary, right? Maybe I overflowed the canary. And how do we know that there is a canary? We can, inside of GDB, type checksec, and we see that there is a stat canary. Alternatively, if I'm on the command line, you can call, let's make sure I'm on the left-hand side. You can checksec, and that will also output the same information. Clearly, checksec is a bit slower within the VM. Insanely slower. I think just all Python has got to be slower. But we see that same information just slightly formatted differently. And so there is a canary. So that's a good thought, right? If we overflowed the canary, then there is this stack check fail that could be occurred. And what happens inside the stack check fail may not be correct, may not comply with setcomp. So that's a fantastic idea. Let's see if we can reason about that. Well, we can use the same thing. We fire it off. Let's confirm and prove what our hypothesis is. Right? Like my initial thought, I wasn't going to go right for the canary. But my initial thought was I just need to set a breakpoint somewhere earlier because I know where execution is good. So the question is, where does execution go bad? Right? And so we can either apply our intuition kind of knowledge of how the program behaves or how processes behave in general, or we can say, hey, I'm not sure what's going on, but using a tool like GDB, we can march forward until it makes sense to us. Right? Like the reason that I know what I know is mostly from marching through in GDB or some other tool until whatever it is I'm looking at makes sense and I understand how those mechanisms work. Like we will use GDB to an insane degree through this course, not because I myself am, the GDB evangelist, but a lot of what we're going to be talking about are various types of memory corruption or dealing with how pointers interact with various regions of memory. And the best way to examine memory is with a debugger, right? Because you want to see it in a running system. Okay, so I'm again at kind of the start here, and my script is blocked on waiting for GDB. Also, I am a GDB evangelist. You are not wrong there. But in this case, it does happen to be the right tool for the job. So we're going to do those same things. I can hit up and go through my history, set follow fork mode child. In this case, we said I want to set the breakpoint somewhere a little bit earlier. If we take a look here at challenge, let's see if we can figure out where the quit occurs. Right? That could be interesting. So, or just noteworthy for people who may not be as familiar with kind of reasoning about disassembly output from GDB. So when we're looking at assembly, the kind of key here is to work backwards. So I know I'm looking for a comparison, a string compare, and so I will find a string compare. I then work my way up because I want to know what the arguments are. Since we know the x86 64 calling convention, we know that we want RDI, RSI, and then possibly RDX. But here we see RDI is RAX. RAX is some value that is on the stack. And then RSI is this value right here. This is a constant that is RIP relative that's being loaded in with the load effective address instruction. So let's grab this address right here. GDB is nice. As I mentioned, this right here is ultimately a constant. GDB will tell us what that value is. So we can copy that right here. And then we can do examine string, paste that value in, and we do see that is the string quit that is being passed to this string compare. Now, if I wasn't right on the first try here, we could definitely scroll up and find another string compare, grab the value again. I just see the string compare. I look up a couple spots to see what values or what addresses are being compared. We grab it. We dump it out here. That's where the run YPU check is, right? And so that isn't too difficult, but I think it's worth mentioning if it isn't something that anyone is familiar with that is still in the course. So we found where this string compare is. So that's going to be at challenge plus 707. So let's set a breakpoint at challenge plus 707. Right? This is the earliest point where our quit kind of comes into play. So we have that breakpoint. I believe I already set follow fork mode. We let the challenge run free. Remember, everything right now is blocked on my script up here on this input line. That's why we see waiting for GDB right here. So even though GDB has continued execution, the script hasn't connected, so nothing has really occurred. I mash enter up here on my script. That fires that off. What do we get? P send line quit. That's all good. Where did GDB go? Oh, I must have not set follow fork mode because I'm still blocked on accept. Lame. All right. Let's do it this time, but do it right. Twitch says they remember the solution now. It's one of their favorites of the module. Yeah, please do not spoil the solution. This one, I think, like I'm pretty sure I'm aware of where it goes, but I'm not purposely like failing to use GDB. But we definitely won't get all the way there. Set follow fork mode child. March forward, let our script run free. What did I go for? 707? It was called string compare. What has gone awry here? Because I would expect to hit that location. Let's think. Oh, wait, now that does send quit in my script here, doesn't it? Send line quit. We send X1000A. We go interactive. What do we got? Breakpoint. Like the person that asked the question clearly sees where this is going, right? Which is awesome. But this is a great opportunity to figure out what I did wrong. Info break. So I did set a breakpoint at challenge plus 707. And when we looked here at challenge, we're at 707. This is the call to string compare. And this is the string compare on quit. So this should get called. And then this is the comparison that causes us to break. Right here, this jump not equals is equivalent to this break. It's just jumping us outside of this while loop. Right, at 733, this is outside the while loop, and this jump am I wrong there? We should still hit this call. We should definitely hit the string compare. This jump not equals goes to 733. 733 loads this value, prints this out, which we saw. I don't think we saw that. Unrecognized trace. Okay. So I was reading the string compare incorrectly. If this jumps, then it continues the loop. And if it doesn't, then we see it's going to pull this value and do the canary check right here. That's why we see the FS register being used. And then the jump to 755 if it's successful, and the jump to 750 to fail if not. That's a weird control flow. Like there's some weaving there. Twitch says or points out that it's not an insanely long challenge. Once you see it, I'm taking it slow so that I can kind of ramble about various things here in GDB, because I know that there are people that are rediscovering race conditions, rediscovering GDB. I'm not worried at all about the person that asked the question. So if anyone does have any additional questions, like throw them at me and I'll bail on what I'm doing here. I'm totally fine with that. I will say that the hypothesis there that the stack check fail is being triggered is a very good one. And the question is just, what am I doing wrong here? I could have like a rogue process. PSA UX, grep. What is this, toddler? And that is what happened. You'll see here, I'm not running anything. When I was talking about like foot guns with IPython, my IPython isn't, I shouldn't have a running process, right? Or you'd think I shouldn't, but I do. Somehow, I already have a toddler sys that is probably listening on that port, which means when I was connecting, the connection was probably going to this guy while I was debugging on the one from IPython. Right? I am not sure like how that happened, but it did. And the reason it happened is because I'm using IPython, right? It's because I'm using an interactive interpreter. If instead I had this as a single script in a file, it would either run, it'd either be running or it wouldn't, right? Python cleans up the processes as the interpreter exits or when the file's done running. But in an interactive interpreter like this, the Python interpreter is always running. So somehow I ended up with a rogue process that I created that just existed. Which is awesome because that is exactly what I was talking about there. As far as don't do as I do, right? Do as I say, not as I do. We said this was at challenge plus 707, and then we will set follow fork mode child. We continue right there. We fire off. All of a sudden, things worked. Twitch has they never realized that, but at the same time, they never write on IPython. And it's not specific to IPython. Like if I, just as a quick aside, if I just typed Python and got the interactive interpreter, the same thing would occur. Like if I say A equals hello, and then I do a whole bunch of other stuff that doesn't matter, A still exists, right? A is being stored within the session of everything that I've ever typed. And so this is particularly dangerous for people that use interactive sessions and they write commands on one line. Like the one good thing that I've done using IPython or using an interactive interpreter here is that you'll notice that I have everything as like one command. It's one multi-line command. Person on 6 said they got a jet. They had a great time. They learned some things. That's the goal. Hopefully we got you through 6 there. But when I hit enter here, all of this occurs at once, right? But one of the things you'll find people that are newer to working in an interpreter or an interactive session like this is they'll type one command after the other. And the problem is that you forget, well, what was R, what was P, right? And all of these things become invisible to you because they were ran on their own line forever ago. So this is a best practice if you are going to, risk it there. But you already saw how that kind of shot me. And so here we are looking at that location. If we examine, say, 10 instructions at RIP, we are on that call to string compare like I expected. So, all right, good. We haven't completely lost our noggin. And what we are interested in right now is, does this cause, let's dump out a few more instructions. Does this cause stack check fail to occur, right? And so we could find this in two different ways. The first way is to examine the bytes that are going to be checked if we already know what they are. And so we can type info frame, and this is going to give us frame data. So we know where the saved RBP is and where the saved RIP is, right? These are not the values. These are the location of the values. So if we look at, for instance, we examine the address that is at this address, double address there. What we see is 61616161. What do we know? What if we examine that as a string? Well, it's a whole lot of A's. And that makes some sense because what did we ram into the process? A whole lot of A's. So we see here that we were able to clobber the saved RBP on the stack frame. The other thing that we can look at as long as we're here is we can look at, well, what is the saved RIP? And it is also A, which makes some sense because if we look at these addresses, the saved RBP is directly behind or in front of, depending, they're right next to each other. The saved RBP is right next to the saved RIP. And so we just wrote A's and blew right past the stack frame and overwrote both of these values. And if we know what the saved RIP does, the saved RIP determines where control flow will go once ret is called. And so this is a very powerful thing to be able to override. The problem is that there is this stack check or this stack canary. And if we figure this out the second way, which again, simple is not bad here. We can just step through. I'm going to next instruction. Step would go into string compare, I believe. So I'm going to go next instruction. Next instruction. Here's that jump, which is not taken because I read that backwards. Right here, we're moving RBP minus 8 into RCX. And if I go past this and we look at RCX, we scroll up a little bit here, we see RCX is A, right? This is the saved RBP that we've now clobbered. This XOR is checking that, I'm sorry, that's not the saved RBP. This is the canary, which we clobbered. And the canary sits directly in front of saved RBP. And the canary is a known value, right? It's hidden away at FS, the FS segment plus hex 28 bytes. And so when this gets XOR'd, this should result in, hey, these are the same values. But it's not what happens. And so instead, we jump right here and get to the stack check fail. We go into stack check fail. So far, so good. We haven't encountered that SIG abort yet. Now we can march our way down here. Okay, now it's going to call fortify fail. We're going to find it. Something in here, and I don't know that it's in the libc message, will trigger some syscall that is not allowed by seccomp. All right, we're going to gamble. Is it inside libc message? It is. So if I would have kept stepping, but I don't want to, repeat stepping through puts, we would see that occurred. Right? So now we have some idea. And the reason that I know it was inside... did I lose? I did. The reason that I know it was inside that function frame, it had to be either in that function frame or something that's called further down the line, because I typed finish or finny, not see or continue, which will just continue execution from that point until the current function returns. Right. So the thing that is getting caught by setcomp is definitely located in that stack check fail behavior. And so that gives us an idea of why we see what we see. And it also gives us an idea on what is the first kind of nugget of wisdom here to solve this challenge, right? It is worth emphasizing, as my last hint for level 6 here, we said that there is a stat canary. We said that we do have the ability to overwrite saved RBP. We do have the ability to overwrite saved RIP. And we also said that this is a fork server. If you have the requisite knowledge, those three things will mean something together for you. That should give you a pretty clear path forward, at least, I'd say, halfway through the challenge. It's a very, very cool challenge. I'm glad that somebody else said that it was their favorite one. With that, I believe I have burned through the Twitch questions there. Coming up on the, looks like, 2-hour mark. Technically, my office hours are scheduled for 1 hour. However, if you guys do continue to, have questions and there are interesting things to talk about, I do not mind running late most of the time. If I do have to cut it short, I'll try and spend more time on the Discord or somehow make myself available to you as well. Because again, I want to help you guys learn, but the material is hard. So if there are no last minute questions here, and I'll ramble here for another 30 seconds or so for the Twitch delay. If there are no last minute questions, we'll leave it there. Shortly after this office hours concludes, I am going to upload the next module. Remember, you do have about 10 days on it. The idea here is, no, you have more than 10 days for the microarchitecture exploitation module. We are running that for 2 weeks, so it's 14 plus 3, I think 17 days. So you do have some time on that. Last time this content was ran through, it was considered one of the more challenging ones, if not the most challenging. We're putting it on the front side here for a couple of reasons. One, it doesn't have any dependencies. So it really doesn't matter if you do it now or you do it at the end of the semester. There aren't, none of the material will help you do it. It stands on its own. And I have made some changes to the material that hopefully make it a little bit easier to understand. If not, let me know, and we'll figure something out here. We got 2 weeks to run through that, so that should be difficult, but hopefully not as time constrained. Twitch says once you get the hang of the micro arch challenges, you realize they're all kind of the same in many ways. Yeah, the changes that I've made so far is I've actually added new challenges, but don't worry when I say that. The intent of the new challenges is to teach. One of the difficulties that we kind of ran into previously was it becomes kind of a draw the rest of the owl kind of scenario, which is frustrating for you. It's frustrating for me. It's a hard thing to debug because you can't debug. You just have to write perfect code. And so I've created some new challenges that hopefully allow you to kind of build up to gain some understanding about the subparts of writing these type of exploits. So with that, I will leave you guys. I do appreciate you all hanging out. If you do have any questions, please post them on the Discord. And I will try and respond as I have time. With that, I will leave you guys. So goodbye and good luck.